Imagine pointing a spacecraft toward the one place almost nobody has ever gone. Not Mars, not Jupiter, not the edge of the solar system. Instead, aim it straight upward, directly above the sun. It sounds almost laughably simple. After all, we've landed on the moon, flown helicopters on Mars, and sent robotic explorers beyond Pluto. Surely flying up should be easier than crossing billions of kilometers through deep space. But this is one of the greatest illusions in astronomy. In reality, traveling directly above or below the sun is among the most difficult journeys humanity could ever attempt. It demands far more energy than reaching many distant planets, and for decades it remained a direction almost completely unexplored. The reason has nothing to do with distance. It has everything to do with speed. At this very second, Earth is racing around the sun at nearly 30 kilometers every second, more than 107,000 kilometers per hour. We don't feel this incredible motion because everything around us is moving together, but every rocket launched from Earth automatically inherits that enormous sideways velocity. Think of it like standing on top of a speeding train. If you walk toward the front or back of the train, you're still moving with it. To jump straight off the side and instantly stop matching its speed would require an enormous amount of energy. The solar system works in much the same way. Every planet travels within an almost flat disk called the ecliptic plane. Mercury, Venus, Earth, Mars, Jupiter, Saturn, nearly every major object circles the sun along this same invisible highway. Because we're already moving in that direction, sending spacecraft to other planets becomes surprisingly efficient. Engineers simply make small adjustments to an already fast-moving orbit. But leaving that flat cosmic highway is a completely different challenge. A spacecraft attempting to travel directly above or below the sun must first overcome Earth's tremendous sideways motion before it can begin climbing out of the planetary plane. That impossible-sounding obstacle has kept one of the most fascinating regions of our own solar system hidden from humanity for generations. And what lies there may completely change the way we understand our neighborhood in space. If escaping the solar system's flat plane is so difficult, it raises an obvious question. What's actually waiting above and below the sun? For decades, the honest answer was surprisingly simple. We barely knew. That may sound unbelievable. Humanity has photographed the icy mountains of Pluto, explored Saturn's rings, and mapped the surface of Mars in astonishing detail. Yet, until very recently, the top and bottom of the closest star to Earth remained some of the least observed places in our entire solar system. We've been studying the sun almost entirely from the side. Imagine trying to understand Earth by only looking at it from the equator. You would see oceans, continents, storms, and changing seasons, but you'd completely miss what happens over the Arctic and Antarctic. You'd never truly understand how the planet's climate works. The sun presents the same problem. Its poles aren't quiet, frozen regions like Earth's. Instead, they're home to some of the most powerful forces in the solar system. Gigantic streams of charged particles blast into space from these regions at speeds exceeding 700 kilometers per second. Known as the fast solar wind, these invisible torrents constantly reshape the environment surrounding every planet. Even more remarkable, the sun's magnetic field performs an extraordinary trick approximately every 11 years. Its north and south magnetic poles reverse. North becomes south, south becomes north. This magnetic flip is responsible for the solar cycle that controls the number of sunspots, violent solar flares, and enormous coronal mass ejections capable of disrupting satellites, radio communications, GPS systems, and even electrical grids here on Earth. Yet the process begins in regions we've only recently started observing directly. The first spacecraft to truly study the sun from high above the planetary plane wasn't launched because engineers built a more powerful rocket. Instead, they relied on one of nature's greatest shortcuts: Using the immense gravity of Jupiter, the spacecraft was flung onto a dramatically tilted orbit, allowing scientists to gather the first direct measurements of the Sun's polar environment. Years later, another mission pushed even further. For the first time in history, humanity finally received genuine images of the Sun's polar regions. The pictures stunned researchers. Instead of calm, orderly magnetic fields, the poles appeared tangled, chaotic, and constantly shifting, revealing that our nearest star was far more complex than anyone had imagined. And as extraordinary as those discoveries were, they hinted at something even bigger. Perhaps the greatest mystery isn't the Sun itself, it's what surrounds our entire solar system. The hidden secrets above and below the Sun aren't limited to the Sun itself. They may also hold the key to answering one of astronomy's biggest unanswered questions. What does our solar system actually look like from the outside? It sounds like a strange question. Surely we already know. After all, we've drawn countless diagrams showing the planets orbiting the Sun. But those illustrations only show the planets. They don't show the true shape of the enormous space our solar system occupies. Surrounding the Sun is a gigantic invisible bubble called the heliosphere. It's formed by the continuous flow of charged particles streaming away from the Sun in every direction. This solar wind pushes outward until it collides with the thin gas that exists between the stars. That collision creates a protective shield around our entire solar system. Without it, Earth would be bombarded by far greater amounts of dangerous cosmic radiation. For decades, scientists believed this protective bubble resembled a comet, a rounded front with a long tail stretching behind it as the solar system traveled through the Milky Way. It seemed like the perfect explanation. Until newer computer models suggested something completely different. Instead of a comet, the heliosphere may be shaped more like a slightly squashed croissant, with two curved lobes extending behind it instead of one enormous tail. It's a dramatic difference. And here's the problem. No one actually knows which picture is correct. Why? Because we've never stepped outside to look. The famous Voyager spacecraft did leave the heliosphere, becoming humanity's first messengers into interstellar space. But both Voyagers exited near the same flat plane where all the planets orbit. They gave us incredible measurements, but only from one narrow perspective. To truly reveal the heliosphere's real shape, scientists need something they've never had before: a spacecraft traveling far above or below the solar system's flat disk, looking back from an entirely new angle. For the first time in history, we'd see our cosmic home the way astronauts first saw Earth from space. One breathtaking view could rewrite decades of scientific assumptions. The only question left is how to reach that impossible vantage point without carrying an impossible amount of fuel. Ironically, the solution begins by flying toward the one place most spacecraft desperately try to avoid: the Sun itself. If you've made it this far, you might be wondering why scientists don't simply build a bigger rocket. After all, if reaching above or below the Sun requires enormous amounts of energy, why not solve the problem with more powerful engines? Unfortunately, space doesn't work that way. Carrying more fuel means adding more weight, which requires even more fuel to lift. Eventually, you reach a point where the extra fuel needed outweighs the benefit it provides. That's why engineers have spent decades searching for a smarter solution instead of a stronger one. Surprisingly, the answer may be one of the most counterintuitive maneuvers ever conceived in space exploration. Rather than flying away from the Sun, a spacecraft would first dive toward it. As it falls inward, the Sun's immense gravity accelerates the probe to incredible speeds, far faster than any rocket alone could achieve. At the precise moment it reaches its closest point to the Sun, the spacecraft ignites its engines. This technique, known as the Oberth effect, allows the same amount of fuel to produce dramatically more energy, because the spacecraft is already moving at tremendous speed inside the Sun's deepest gravitational well. Instead of wasting fuel fighting Earth's sideways motion, the sun's own gravity becomes the spacecraft's greatest ally, slingshotting it onto a steep trajectory above the solar system. Some scientists are also exploring another remarkable technology: solar sails. Instead of relying on fuel, these enormous reflective sheets harness the tiny but continuous pressure of sunlight itself. Every photon striking the sail delivers an almost imperceptible push, but over months and years, those gentle nudges steadily reshape the spacecraft's orbit. It's an incredibly slow journey, yet one that could eventually tilt a spacecraft far above the ecliptic without consuming propellant. Future missions may even combine both ideas, using a solar sail to spiral closer to the sun before performing an Oberth maneuver for the final climb. If such a mission succeeds, humanity could witness something no eyes have ever seen: the solar system from directly above. We would watch the planets circling the sun as a thin, glowing disk, observe the heliosphere's true shape, and finally uncover what has remained hidden above and below our star since the birth of the solar system 4.6 billion years ago. Sometimes the greatest discoveries aren't waiting at the edge of the universe. They're hiding in the one direction we've almost never traveled.